The arrow problem: why time flows one way. If entropy is counting and records make arrows, here's the stake. Memory, causation, responsibility, they all lean on one direction. You remember breakfast, not dinner 3 days from now. You can apologize for last night. You can't pre-apologize for next Thursday and make it land. If the microlaws are reversible, why does your life feel welded to one timeline? Start with the clash. Newton's and Schrödinger's equations run clean in both directions. Reverse velocities in a billiard simulation or complex conjugate a wave function, and the math rewinds. Meanwhile, thermodynamics says coffee cools, eggs scramble, iron rusts. In the 187th, Joseph Loschmidt posed the paradox plainly. If the laws are time-symmetric, why don't we ever see a scrambled egg unmix? Boltzmann answered with typicality. From a low-entropy macrostate, most microstates evolve toward larger phase space regions. But typicality piggybacks on a special past. Without that past hypothesis, a very low-entropy beginning, you don't get the arrow you live. Now take it personally. Memory is a physical record, not a ghost. Neurons strengthen synapses. Photons scatter off a notebook page. Hard drives flip magnetic domains. To store a bit, you eventually erase a bit, pay Landor's cost, and dump heat. That heat isn't side noise. It's the bill that keeps arrows honest. Your recollection of a promise is tied to entropy you exported when you wrote it down or rehearsed it aloud. If the past were as plastic as the future, those records would reverse too. They don't, they accumulate. A human moment, you open your freezer. Cold air spills, your skin prickles, the compressor kicks on. The fridge isn't making cold. It's pumping entropy outward, riding a gradient, paying in electricity and heat. Local reversal funded by a larger increase. That's the arrow braided through daily life. The same braid holds your inbox. To reduce clutter meaningfully, you spend attention and burn glucose. Organization is purchased. But this still dodges the unnerving bit. If microlaws are reversible and decoherence is just entanglement growth, why don't we witness large-scale unscrambling? Because records don't stay local. Once information about a configuration has spread into zillions of degrees of freedom, air, dust, radiation, the alternatives that could interfere are functionally gone. Not destroyed, exiled into correlations across a space you can't access. You could, in principle, recohere a shattered vase by reversing every environmental interaction. In practice, you'll never gather the photons that carried the news of the break. Information that escapes becomes context, and context picks the story. Meanwhile, something else anchors the arrow. Causality is geometric. Draw your light cone. Events inside your past cone can touch you, events outside can't. That cone isn't negotiable. It's light speed carving the network of influence. Temporal order outside each other's cones is frame-dependent, but inside cones, before and after have teeth. Every real cause you name is a chain of records propagated within cones. Reverse the chain and you run into missing links, signals that never existed because nobody paid the cost to create them. Loschmidt's punch still stings. If you could prepare the right microstate, velocities tuned just so, the air in this room would gather in a corner and chill your hand. Physics doesn't forbid it. Preparing such conspiratorial conditions would require mirror precision control over every prior interaction. That control is another ledger. Specificity is expensive. The arrow hides in the price of precision, not in a mystical push from time. Then the trap called the Boltzmann brain. In an equilibrated universe, rare fluctuations could briefly assemble minds with fake memories, far more often than whole low-entropy histories like ours. The fact we perceive a vast, consistent past argues we're not such fluctuations. It nudges us back to the past hypothesis. Our cosmic initial condition was astonishingly simple, and inflation likely spread that simplicity. Compression followed by expansion, writing a minimal program whose output looks like a rich history. In that frame, the arrow isn't stamped on equations. It's a boundary condition plus a planet of record makers generating heat as they copy and recopy. Here's where it gets practical. Causation isn't metaphysical oomph, it's stable counterfactuals in a noisy world. You act from reasons because your brain is a prediction engine exploiting gradients and redundancy. Responsibility lives in engineering. Did you set conditions so reasons you endorse win more bids? Sleep, social contracts, institutional scaffolds. These tilt thresholds so histories that keep paying forward beat histories that burn out. The arrow gives you leverage if you acknowledge the ledger. One last scene. A physics lab runs a spin-echo experiment. Random interactions scramble nuclear spins, signal fades, the arrow in miniature. Then a timed pulse flips phases and the signal reappears, a ghost of order recovered. You can claw back structure locally with care and cost, but the lab closes, the building radiates heat, the Earth beams infrared into space. Arrows braid, local reversals riding on global increase. The future isn't written by entropy alone. It's negotiated by who pays to make which records stick. Black hole thermodynamics, when entropy gets a new boss. Meanwhile, the ledger we've been teasing shows up where gravity draws a hard boundary. A black hole isn't a thing in the everyday sense. It's a region with a rule. Cross the event horizon and no causal signal returns. That rule turns entropy from volume counting to surface bookkeeping. The stakes couldn't be higher. If horizons set budgets, then our doom story forgot who holds the wallet. Action first. In 1972, Jacob Bekenstein asked an uncomfortable question. If you throw a cup of coffee, full of heat, molecules, information, into a black hole, doesn't the second law flinch? Outside, entropy goes down. His fix sounded like heresy at the time. Assign the black hole an entropy proportional to its event horizon area, not volume, area. Then in 1974, Stephen Hawking did the unthinkable calculation. Quantum fields near the horizon don't sit silent. They generate radiation with a thermal spectrum. A black hole has a temperature inversely proportional to its mass and radiates like a body with entropy S equals A4 in Planck units. The heresy became a theorem's whisper. Horizons are thermodynamic. Impact immediate and weird. Surfaces tally bits. The bulk obeys the boundary ledger. That flips every instinct. Double the mass, the area doesn't just double, it scales with mass squared. Your intuition that more inside means more entropy fails. The horizon area is the book's cover. The interior chapter count never lands on your desk. That's the generalized second law. The sum of the outside entropy plus the black hole's area entropy never decreases. Toss in your coffee. The horizon grows enough to pay the bill. No cheating, just a new accountant. Micro story. A graduate student stands on a catwalk above a ring of liquid nitrogen tanks in a cryo lab. They joke about tossing a hot mug into one to see the boil. The advisor grins, then sketches a black circle on the whiteboard. Do it here instead, he says, and the area goes up more than your steam cost. Outside looks tidier because the boundary paid extra. The student nods at the absurdity that lands a sense. The book never loses pages, it moves them to the cover. But there's a complication sharp enough to cut the subject in half. Hawking radiation is thermal, featureless. If a pure quantum state collapses and the whole evaporates to a mixed soup, information seems gone. Unitarity, the promise that quantum evolution preserves information, would break. That's the information paradox. We either scorch quantum mechanics or rewrite our gravity storytelling. Decades of argument followed. Before we jump to modern resolution attempts, feel that crisis where it lives. A horizon with a temperature means a horizon with microstates, but we don't know their identity in our universe. In toy worlds, anti-de Sitter spacetime, holography gives a dual quantum theory on the boundary that counts them. In our de Sitter-like cosmos, the dual is unfinished. So the area law is a lighthouse, bright, reliable, distant. It guides, but we haven't reached shore. Now the generalized second law plays like a courtroom drama. Drop a memory stick into a black hole. Out here, your records decrease. The horizon grows by an amount set by energy and redshift. The sum increases. Later, as the hole evaporates, outgoing radiation carries entropy away. Early on, that radiation's entropy rises. It looks even messier outside. If the process were truly thermal to the end, the outside would be left with noise and no imprint of what fell in. That would shatter the global ledger. Meanwhile, something else is happening across town in cosmology. A universe with accelerated expansion has a horizon too. Gibbons and Hawking showed de Sitter space has a temperature and an entropy proportional to its horizon area. Not just black holes, cosmic horizons also keep accounts. Your causal patch has a finite bit budget scaling with its edge. Facts stabilize inside. Beyond, correlations can't be fetched. The ledger is patch-bound, not parochial. That echoes our claim. What you can copy and cross-check depends on access. Horizons are the access policy. Back to the paradox sharpened. If the horizon encodes the missing information, how does it get out? Hawking's original calculation ignored back reaction and entanglement structure at late times. The outside modes were entangled with interior partners, not with early radiation. If that stayed true throughout, late radiation couldn't also be entangled with what already escaped. Quantum monogamy would be violated. The neat horizon would have to become a firewall, torching smoothness to protect unitarity. No one liked that. The equivalence principle, the promise that free fall is dull at the horizon, would fail. Here is where the new boss flexes differently. Counting by area suggests that what we call inside may be a story told from outside via correlations. The ledger lives on slices of geometry, apparent horizons, extremal surfaces, that decide which degrees of freedom you're allowed to reconstruct. You don't need to post a guard at the horizon. You need to count correctly. This is the seed of a resolution. Redefine which region's entropy you're measuring and when, and the ledger balances. One more human beat. A computational physicist stays late, running a toy model of a black hole coupled to a radiation bath. The plot on her screen shows the radiation's entropy rising, cresting, then bending down. She exhales a laugh in the empty office. "Okay, boss," she says to the flat, glowing curve. "You win. Surface first." The black circle on her whiteboard suddenly looks less like a hole and more like a vault door that also prints receipts. Moral is blunt. Horizons don't repeal the second law, they complete it. They change the units at the edge and force us to count entanglement, not just molecules. The doom story shrinks again. The rule is everything decays to featureless waste. It's everything the ledger lets you access tends toward typicality, unless the boundary has room and a mechanism to store structure. Black holes make room. And in the next act, the curve that bent on her screen will tell us why nothing was truly lost. The page curve in islands. Ledger balances after all. This was the moment the ledger blinked and changed hands. For decades after 1974, Hawking's calculation said the entropy of Hawking radiation just climbs, straight line, no bend, until the black hole is gone. Translation: outside looks noisier forever and the story of what fell in never comes back. If that were true, the global book wouldn't balance. Unitarity would break. But the new boss, surface counting, entanglement, horizons as interfaces, hinted we were holding the wrong ledger at the wrong time. Action first. In 1993, Don Page made a daring forecast based on simple quantum bookkeeping. If evaporation is unitary, the fine-grained entropy of the radiation shouldn't climb forever. It should rise at first because early photons are entangled with the interior, hit a maximum at roughly the halfway point in evaporation, the Page time, and then fall as later radiation carries out correlations that complete the record. Plot it. A hill that crests and returns to zero. That's the Page curve. Hawking's straight ramp had to bend. But nobody knew how to compute that curve from gravity itself. The breakthrough arrived with a magician's modesty. Don't add new physics. Count the right region. Using ideas from holography and quantum extremal surfaces, theorists defined the entropy of radiation not by naive partitions, inside versus outside, but by extremizing a generalized entropy that includes an area term plus bulk entanglement. Early in evaporation, the dominant surface excludes the interior. The radiation entropy rises. After the Page time, a new surface, an island just inside the horizon, enters the game. Now, when you compute the radiation's entropy, You include the island's degrees of freedom as effectively part of the radiation's entanglement wedge. The curve bends down. Ledger balanced. What's an island in plain speech? It's a region that you, as the accountant of the radiation, are allowed to reconstruct from the correlations you already hold, even though it sits behind the horizon for someone else. Think of it like this. You've been quietly collecting scrambled printouts for years, early hawking quanta. Alone, they look like noise. But after enough pages pile up, a pattern emerges. A new set of missing pages, the island, becomes recoverable in principle from your archive. Information wasn't destroyed. It moved its address on the ledger. Micro story. A grad student schedules midnight printer time to push through the island papers. She highlights a line, sketches a little worm of an extremal surface on scrap, and watches a plotted entropy that rises, peaks, then falls. She whispers, "The curve finally bends." Relief, then a headache. If islands rescue unitarity, what happens at the horizon for someone falling in? Smooth or a firewall? Impact immediate. The page curve computed with islands matches the quantum expectation. Unitarity wins. No net loss of information. The ledger doesn't leak, it reallocates. Bits that look trapped behind the horizon are, after the page time, effectively encoded in radiation correlations you can access in principle. That's the Hayden Preskill mirror intuition sharpened. Toss in a diary after the black hole scrambles, wait a scrambling time plus some. Then, with an absurdly powerful decoder, you could, in principle, extract the diary from the outgoing stream. Nobody's building that decoder this century. That's fine. Physics only needed the book to balance, not a thief to read it. But there's a complication that refuses to leave quietly. If late radiation is highly entangled with early radiation to recover information, how can it also be entangled with interior partners behind a smooth horizon? Quantum monogamy says it can't be maximally entangled with two independent systems. That's the firewall puzzle. One door invokes state dependence and quantum error correction. Bulk operators behind the horizon are reconstructed from different boundary subspaces depending on the global state. No illegal cloning, just clever encoding. Another leans on complementarity. No single observer can verify both the smoothness and the detailed decoding. For the infaller, the horizon stays dull. For the distant archivist with impossible patience, the news is in the radiation. Same backend, different dashboards. Meanwhile, the island rule generalizes beyond black holes. Cosmological setups with horizons inherit similar bookkeeping. What counts as the system depends on your patch, your access, and the extremal surfaces that fence your wedge. Entropy becomes less a measure of universal mess and more a policy for which correlations are stably accessible to which observers win. That's the real flip. The second law didn't lie. Our picture did. We forgot to ask whose ledger, over what region, and on what schedule. Here's the stake that loops back to agency. If information can be hidden, transferred, and later recoverable by the right collector with enough redundancy, then what you stabilize matters. Redundancy wins. Copy storms make facts subjective. Waste dies because nobody pays to keep it. The universe doesn't keep every detail explicit all the time. It stores minimally and encodes cleverly on boundaries. Efficiency is the law behind the laws. One last human beat. A theorist pushes back from his desk at dawn, knuckles aching from algebra. On the board, SR up, crest down, a tiny island like a lifeboat just inside a horizon. He texts a colleague, ledger balances. Then adds, about that firewall, the reply pings, different dashboards, same backend. He grins, kills the lights, and leaves the curve glowing on screen. The first honest plot of nothing was ever lost. Holography, surfaces encode the world. Here's the pivot that sounded like science fiction and then refused to let go. If black holes keep their books on the horizon, maybe nature does that trick more broadly. Not we live in a simulation, but a harder claim. The right surface, with the right rules, can encode what happens in the volume. Holography isn't a metaphor. It's a working lab for gravity. Action first. In 1997, Juan Maldacena uncovered a shocking equivalence now called AD-SCFT. Take a universe with gravity living inside a negatively curved bulk, anti-de Sitter space. Put a quantum field theory without gravity on its boundary, one dimension down. Against every instinct, the two descriptions match. An excitation on the boundary maps to a ripple in the bulk. A black hole inside corresponds to a hot fluid outside. A dictionary, not a slogan. Geometry here, entanglement there. Impact immediate. The area law we met at Horizons wasn't a one-off. In holographic ground states, the entanglement entropy of a region scales like the area of its boundary, not its volume. In 2006, Shinsei Ryu and Tadashi Takanagi sharpened it. To calculate the entropy of a boundary region, find a minimal surface hanging into the bulk whose edge matches the region's boundary. Its area, divided by 4 in Planck units, gives the entropy. Surfaces, again, tell you how many bits belong to a chunk of the world. Glue regions together and those minimal surfaces rearrange. Connectivity in the bulk mirrors who shares information on the edge. Space looks stitched from entanglement. Micro-story. A coder sits in a dim apartment, watching a tensor network visualization breathe. Nodes flare, links thicken, the web flexes like a lung. She drags a slider. A ragged room reassembles from seams, edges first, interior second. It's like the wallpaper renders the furniture if the seams line up, she mutters, then laughs. The math doesn't simulate a house. It simulates a toy holographic code where losing some boundary patches still lets you reconstruct simple bulk operators. That resilience isn't magic, it's error correction. That's the next reveal. In good holographic toy models, the bulk-to-boundary map is an error-correcting code. Bulk information is redundantly encoded across many boundary degrees of freedom, so you can lose parts of the edge and still recover the interior. That's why horizons can stay smooth for infallers, while distant decoders reconstruct behind the horizon operators from different boundary shares. No cloning. Different reconstructions from overlapping datasets. Complementarity gets teeth. But there's a complication we can't dodge. Our universe isn't anti-de Sitter. It looks more like de Sitter, positively curved, expanding, with a cosmological horizon no one has fully dualized. The clean AD-SCFT dictionary doesn't copy-paste. Even so, area laws keep showing up. Ground and low energy states obey them. Quantum matter across scales exhibits entanglement that hugs boundaries. The page curve and islands rely on extremal surfaces that echo Ryu, Takanagi in spirit. The pattern is loud even if the exact dictionary is missing. Meanwhile, something else hums across town in quantum Darwinism. Decoherence doesn't just kill interference. It spreads pointer information into many environment fragments. Multiple observers read the same story from different shards. Photons bouncing off a table, dust grains, air. That redundancy feels wasteful until you remember error correction. Copy storms stabilize facts. The world looks crisp because the same bits are recorded many times on accessible surfaces. The light that reaches your eyes, the pressure waves that hit your ears, the voltages a sensor reads. Objective reality is a hologram in practice. Details ride interfaces that many can query. Here's the stakes line that bites our doom story. If bits scale with area, not volume, full volume entropy was the lie. You never had the budget to store every microscopic detail explicitly. Nature saves by committing what can be asked and inferred within horizons and leaving the rest implicit, constrained by symmetries, redundancies, and consistency. That's compression with receipts. You don't lose predictive power because the questions you can physically pose don't require the missing bits. Efficiency as policy. Micro-story. A telescope team dials in an observation near a galaxy cluster's rim. Their lensing map, just a distortion pattern on the sky, reconstructs a mass distribution they'll never touch. It's like the edge told on the middle, a postdoc says. The pi nods. Holography is a habit long before it's a theorem. They don't mean AD-S, they mean a practice. Measure boundaries, invert constraints, extract the interior to the precision the data allow. Complications deserve honesty. ADS holography is exact and spectacular. For our de Sitter-like patch, we have hints, not a completed duel. Any confident the universe is a hologram claim outruns the ledger. Still, the discipline pays off even without a perfect dictionary. Entanglement builds geometry and models. Minimal surfaces compute entropies that match page curves. Quantum error correction explains how interior operators evade firewalls for honest observers. And the area law keeps whispering, budgets live on edges. Now haul this back to agency. If surfaces decide which bits stabilize, then efficiency, minimal commit, maximal redundancy, chooses what the world keeps. Facts that spread across many channels survive. Ones that don't fade. Institutions that copy, verify, and archive earn reality's attention longer than ones that hoard. Physics isn't moralizing. It's offering leverage. Push information to interfaces others can reach, and it persists across bad weather and time zones. A last beat before we lift our eyes to the sky. Holography reframes inside and outside as viewpoints tied to access. The boundary isn't a wall, it's an API. Change your access, change the code path that reconstructs the bulk. Different dashboards, same backend. That's not mysticism. It's the price of living where counting happens on edges and meaning travels with redundancy. And it sets up the next move.